So this is a video talkthrough of Workshop 5 for OS202. We're going to be following through the steps given in the associated document and ending up by calculating, importing some tidal height data for 1 year. Then we're going to be calculating the tidal constituents for this year of data, and then predicting what the tides should have been if they were generated by the gravitational forcing, and then calculating the difference between our gravitational prediction and what was actually measured, which is then the non-tidal effect on the sea level height. In this case, it's atmospheric effects such as air pressure and wind. But we'll look in more detail at those as we go through. So we've downloaded the data that's been packaged. It's been in turn downloaded from BODC, and I would encourage you to have a look at the BODC website. And we're going to be using the UTide toolbox, which is found on the MATLAB file exchange. And again, I'd encourage you to have a look at the MATLAB file exchange and what resources are available on there. So I've downloaded the Workshop 5 folder to my desktop. In MATLAB, I'm going to change into that folder, and within that there are two subfolders. One contains the data files, and the other one contains the UTide toolbox. I'm going to just right click and then make a new folder which I'm going to call M files, and this is where we're going to save the functions that we're going to make during the session, and then I'm going to right click and add that to my path, so that when I'm in one of the other subfolders I'll be able to access the files in there. If I change into the data folder, then the first thing we need to do is to have a look at the data that we're going to import. And this is tidal height data from Devonport for each of the years that are given. So that's year 2000 through to 2015. Now, if we have a look at one of these files, it's a plain text file, so I can just right click and then click open. Then the MATLAB editor will pop open and it will show you what the data actually looks like. And in this case we've got some header lines, and then we've got the data that we actually want starting at line 12, and you can see it's made up of a line number, and then we've got a date, a time, and then we've got the number that we want, which is the sea surface elevation, and then we've got the data center's calculation of the residual, which we're not going to be looking at. We're wanting to import this elevation and the date and the time only. Now you'll see here that we've got a value of -99 and the letter N at the end of that value, so we first need to understand the format of the data, and that's given in this format.pdf document, which I can open outside of MATLAB, and this display contains a description of the detail of the values in the file. So it explains the values that we're interested in, the time, and then the sea level value in this particular column. But then it also explains those letters. So letters M, N, and T are basically values which are deemed to be either null or improbable or have been interpolated. And so when we import the data, we want to do a quick quality control and then set any value with an M, an N, or a T at the end of it to a MATLAB not a number. So these values should be imported as not a numbers rather than -99s. Okay, so we'll just talk through the process of importing the data file. We need to open the data file in MATLAB, which is what we've just done here. We then need to read the header lines until we get to the 12th line of the file, which is where the data starts. And then once we've read the 12th line of the file, we then read each line in turn and end up importing the date, the time, and the value that we're interested in. So to do this, and because there's about 15 data files so far, but if you were choosing a different port there could be 100 data files, what we're going to do is to create a new function. So I've opened up a new file, and I'm going to call it, I'm declaring it as a function. It's going to output some data that I've loaded, and we're going to call it load tide data, so that it's fairly explanatory what it's going to do. And I'm going to tell it the name of the file that I want to load the tide data from. I'm then going to put a comment in, which will be function to load tide data from BODC data file. So this will appear when I type help and then load tide data from the command line. Before we go any further, I'll save this, and I'm going to put it in my M-files folder that I created and added to my path. It's already given the correct file name, which is load tide data, and so I'll save that. Now, the first thing we need to do is to open up the file that we've passed into this function. So we'll do fopen, which opens that file, and we'll be opening file name, which is the name of the file that we've passed into the function, and I need to give this a name. So the output of the fopen file is it's an identifier to the file that you just opened. So I'm going to call it FID for file identifier. And at the end of the file, it's useful to close the data file as well. It's good practice to do that. For example, you might have thousands of data files open, and if you don't tidy up after yourself, then that can slow some computers down. So at the end of this function, once we've done whatever we want to the data file, we'll close it again. So when we looked at the file ourselves, we opened it up. We then started reading it line by line, and that's exactly what we'll tell MATLAB to do. So to read a line, we use fgetL for file get line, and then FID tells it which file to get it from, and we'll give that a name. So I'll call it temporary line equals fgetLine FID. So that will read one line of data, which will be this first line. But what we want to do is to read 12 lines, and that would then give us the first line of data. So if we read 12 lines one after the other, we can use a for loop. And we can say for I, so I is just the name of a counter that I've created, I equals 1:12. We'll go around this loop 12 times, and then I indented the T line equals fgetLine just to make it look neat, and we put an end at this point. Now, if I type T line here without a semicolon on the end of it, then it will just display this last line that has been read from the file. So if I save and then go to my command window, and then to run that function that I've just created, I type load tide, press the tab key, and MATLAB, because it knows it's in its path, will complete the rest of it. And then the file name I'm going to open is 2000 dev.txt. And what this should show being displayed is the first line of data. So it skipped over the first the header lines, and we've now got the line of data that we want to start doing stuff with. Okay, so we know that it's got to the point that we thought it was going to get to, so I can just delete that line because we've done a sanity check on it. The next thing I want to do is to create another loop which is going to read line by line all the way through the data file. So I basically want to copy this command where we read a line, so we'll use that again, and we're going to put it in a different kind of loop, which is going to be a while loop. And we're going to say basically, well, while we don't reach the end of the file, then keep on reading lines of data from the file. So a while loop, again, I would indent it, and I'll put an end which then says run these commands over and over until a particular condition is met. And the condition that we're going to use is char tline. Now char is a MATLAB built-in function which basically says, have you got text given back to you by this getLine function. So if you're yet to reach the end of the file, then fgetLine will give you the next file, the next line of text from the file. But when you get to the end of the file, then fgetLine, instead of giving you text, will give you the number -1, at which point char of -1 will be false, and that means that this loop will exit, and then you would close the data file and then exit the function. So this is basically a check of have you reached the end of the data file. Now, the other thing we also have to say, double check, is that occasionally some of the data files have got a blank line at the end of the file. So we need to just make sure that the length of tline, the line of text that has been read in, is greater than 0. So we need to make sure that it's not empty. So we can say and not is empty tline. So this is saying, is it a character, so is it text, and is it not empty, so is there actually text on that line. So if I save that and then I switch back to this command window, I can rerun this, and that has now read the file and it's exited without an error. Similarly, I can run all the other files through and it can exit without an error. I'll go back to the year 2000. Okay, so we've read all the lines in the text file, but we haven't actually done anything useful with them yet. Next thing I'm going to do is just to copy this line of data into my load tide data function so I can see what I'm going to do with it. So I'm just going to comment that with the %, so that I can see, once I've got my data, how do I actually convert it to something useful. So what I'm going to say is we need to get this line of text broken down into the different chunks that it's made up of. So we've got a line number, which we don't care about. We've then got the date, the time, then the value we're interested in, and another value that we're not really interested in. So I need to break this line of text down into the chunks, and I use the MATLAB function text scan to do that. So text scan, and then you give it the line of text, tline, and then you tell it the format of the information that's coming in. Now, although we've got numbers here, we've also got mixed in with that different characters. So we've got slashes and we've got these flags that we then want to be dealing with. So I'm basically going to say that we've got 1, 2, 3, 4, 5 chunks of information which are going to be characters or strings of characters which are separated by spaces. So I'll do and the it's called the format specifier to say that this is a chunk of characters or a string of characters is %s. So this is saying break t-line down into 5 chunks of characters or 5 strings, and I need to assign that to a new variable which I'll call temp for temporary, and this will just contain the chunks of information on this line. I can then start doing something useful with these chunks of information. Now the first chunk is the line number and we're just going to discard that, but the second and third chunks of information are the date and time, and we want to stick those together into a MATLAB timestamp or a date num. And so we're going to create a date num, so using the date num function in MATLAB, which is made up of the second and the third elements of this output of the TextScan command. So, and then we're going to call that data dot, we'll call it date time equals, so this is just the timestamp that we've output from date num, and is made up of these two groups of the or chunks of information on this line. Now what's slightly complicated is that TextScan is able to output numbers and strings or a combination of both. And to do that, it uses what's called a cell array. And a cell array is different to a normal matrix in that it can be made up of different types of data. And to access the different bits within a cell array, instead of using round brackets, you use curly brackets. And so I want the second cell and the third cell of information out of this. So that's the date, and then the time is the second cell of the output cell array and the third cell. And I want to stick those together. So to stick or concatenate things together, you use square brackets. So I'm now sticking those two things together, but I want to make sure that there's a space in between them. So I'll put a space in between single quotes. And the final thing I need to do is it's going to export these as cells, but I want to turn them into strings. So I'm going to do cell to mat, which is a function which converts a cell into its native format. And again, I have to do it here. So we've got cell to mat. So we've ended up with quite a long statement with many different kinds of brackets. There's all the different kinds that we've got, but it's basically taking the second chunk of information from this line and the third chunk of information from this line, is converting both of those to strings, and it's then sticking them together with a space in between them, and then it's using the datenum function to convert that into a timestamp. I'll put a semicolon on the end so again it doesn't dump to the screen. The next thing we want to do is to deal with this fourth chunk of information on that line, which is a number, and then it has a letter after it. And so we want to basically convert that into a string. So I can say temp equals, and I'm just going to use this cell to mat function we've used here, and then I'll say temp and then 4. So that's basically saying convert the fourth chunk of information into a string from being a cell or a container of information into a string. Now we can then say, well, if the last character of this string is equal to an M, an N, or a T, then we want this number to be assigned to be a not a number. So I can say if, and then TMP end is equal to N, which is this null value, and then OR, which is this vertical bar. On some keyboards it's 2 lines above each other, and it's normally shift and then backslash. So this is a logical OR. So this says if the last letter of TMP is an N, or if the last letter of TMP is an M, or the last letter of TMP is a T, then our output, which is data dot elevation, equals not a number. Otherwise, or else, data dot elevation equals, and then we need to convert this string into a number. So you use str to num, which is a MATLAB function to convert a string of characters into an actual number, and it's TMP that we're converting. And then I do end. Okay, so we've opened the file, we skipped over the headlines, we're then reading down each line in turn until we get to the end of the file, and we then break the line into chunks, and we then extract the date and time and make a timestamp, and then we check to see whether we've got a null value and assign a null value here, and when we if we don't have a null value, then we assign it the actual value, and then we go around and get the next line. Now the problem we've got is that when we've read the next line, we go back through this loop, we break the that line of text down into its constituent parts, but currently we would overwrite the data that we've just read from the preceding line. So what we need to do is to add in a counter. Now I can reuse the counter that I've used here, because it's not used later on. So I can just say, but I need to make sure that I reset it. So I say I equals 1, and that's reset the counter. And then I can say that for each time we go around this loop and we read a new line of data, I'm going to add I equals I plus 1. I'm going to add 1 to the line counter, and then I'm going to put the next line of data into the next element of the output arrays. So it's the date time I, it's elevation I, and elevation I here. We're just about ready. The final thing that we can do, which can be useful, is that this output data and date time is useful, is a single structure, and it's useful to label that with the file name that we've read in. So if we say data dot file name equals file name, that means that we've copied the information of which data file we're dealing with back into the output data structure. So if I save this and then I go to my command line, now when I run it, I want to actually do something with the output from the function. and I want to give it a name, so I'm going to say data 2000 equals load tide data 2000 dev.txt. So I could now rerun this function on different data files, and I would give the output an appropriate name. So if I press enter at this point, it takes a short while to run because it's reading through many thousands of lines of data and it's checking to see whether they're null values. And what we should see is this data structure that we've created, which has been output from the file, and it's got these elements within it. So we've got the file name, we've got the date time, so there were 35,136 lines of data in this data file, and so you've got the timestamps and the elevations. Now what we can do is we can do the first of the plots that we saw in the file here. So this time series plot of the sea surface elevation with appropriate labels. Now to do that, I'm going to create a new function, and I'm going to give it the data that we've just loaded. So again, I can rerun that function without having to edit the names within it. I'm going to get it to automatically pick up the file name, for example, and apply the right labels. So if I go back to my editor and then I start a new file, this is going to be again a function, and it's going to plot the tide data. So I'm going to call it plot tide data. Then in brackets, I'm going to give it the data that I want to be plotted. And I'll just put a single line of explanation, function to plot BODC tide data loaded with load tide data function. I can then save this, and I'm again going to put it in the mfiles folder. So I'll save that. And what we're going to do is to change to figure 1. We're going to clear the figure. We're then going to plot data dot date time and data dot elevation, and we're going to make a blue line to do that, and then we're going to do date tick to give nice labels on the x-axis, and then y label is the sea surface elevation in meters, and the title will just give us the file name. So that's data dot file name, and sometimes file names can have underscore characters in them, at which point it would mess up how that was displayed, because MATLAB normally interprets an underscore as a way of making a subscript. So I then say interpreter and then none, and that just ensures that a file name isn't changed. So if I now save that, go back to my command window, and then I can do plot tide data, and then the data that I'm going to plot is this data 2000 data structure that we created from loading the tide data. That then brings up my figure window, which is nicely labelled with a title on it, and you see the spring tides, the neap tides throughout the year of year 2000. Now, the reason we've created functions is that we've got a lot of these data files. So to load up, say, the year 2015, I can do data 2000, and I can just edit the input file and also edit the name of the file that is going to be output. And again, it will take a short while to read all of the data in the data file. So we've got 35,040 data points in this case, and then I can plot that data with my plot type data function, but change the input data to 2015, and this now is the 2015 data. So you can see that the data coverage is much better. There are fewer gaps in the data, but there is still a gap here when there might have been a fault with the tide gauge. Okay, so we've created a function which will load the data file, and this load tide data, the approach that's been taken here is similar to the approach that you could take with just about any kind of data file. Having a loop, which is checking for the end of the data file, and then reading in line by line, and then splitting that information down into its component parts, allows you to really access any text file that might contain a sequence of data. So the next thing we're going to do is to take this real tidal data, which shows the springs and neaps, and also, if we zoom in, the individual tides within the day, and we're going to use this as the basis of a prediction of what the tide should have been over the course of this data set. So particularly if I switch back to the year 2000 data, where we've got quite large gaps within the data set, it could be that we're interested in, well, what should the tides have been during these periods? And we can use a toolbox to enable us to do that. And the toolbox is called UTide. We've seen that it's available on the MATLAB file exchange, and it's within the Workshop 5 folder. So if I change back to that and then change to UTide current version, which is the system, the toolbox that was downloaded from the file exchange, then we can see that it's made up of a map file which contains information on the tidal constituents, and then it's got these two functions, and we're going to run the solve function to solve for what tidal constituents there are in our data set, and then we can predict what the tide should have been using this reconstruct function. Now, there's very comprehensive instructions in this PDF document that's also been provided. And so if you open that outside MATLAB, then you can see that it's a 60-page document which tells you all about, well, how does the system work, and what is the actual way that it does the calculations of the tidal constituents within the data that's been provided. Now, it's a very comprehensive document. My suggestion would be that if you need to do a harmonic analysis, a tidal analysis of data in the future, that you might want to look at the details of this. But the information that's needed for what we're doing is later on there are some detailed usage instructions, and particularly in the different methods that can be applied to the data and the output information that's also provided. So here from page 40 onwards, it actually tells you about the MATLAB functions that have been provided, and there's a quick start guide on how you can go about using it. Now it can be used to actually calculate the tides from velocity records as well as elevation records, and so we're going to be using this format of the commands to solve and then reconstruct or predict what the tides should have been. So the first step of running our tidal constituent analysis is to run the utsolve function. So I can type utsolve, and then I've got to tell it what data I'm going to be working on. So it's looking for the time, and then it's looking for either the u velocity and the v velocity, but I'm going to be using the elevation and then just an empty placeholder, and then you tell it the latitude of the measurements, and then you tell it which constituents you want, or you can say that you want it to work them out itself. So I'm going to put all those input arguments in, and then I'm going to have the output called coef for the coefficients that this function is going to solve for, and it needed the time, which was the data 2000 dot date time. It then needs the elevation, so that's data 2000 dot elevation, and then it needed a placeholder because we're calculating from a single elevation rather than a eastward and a northward velocity components. I then need the latitude. Now the latitude is given in our data file here, and it's 50.36839 is the latitude of the tide gauge. So I put that in, and then I put in the word auto, which makes this solver work out which constituents are actually appropriate to be included. And again, I'd refer you back to the instruction manual if you wanted to specify a more limited number of tidal constituents. Now we can run the solver and assign the output to the new variable coef, and so I'll press enter, and we get some output saying the solver is preparing a matrix. It's then calculating the solution, and then it will display some diagnostic information in the command window for us. So what we have here are two tables of information. The first one lists for each of the tidal constituents the amplitude of the tide that can be attributed to it. So the M2 and the S2 are the principal semi-diurnal lunar and solar tides, and at Devonport they have an amplitude of 1.68 meters and 0.604 meters. The other two main semi-diurnal constituents are the N2 and the K2, and they're to do with the shape of the lunar orbit and also the declination of the Earth, Moon, Sun system. And the M4 component is a higher harmonic of the M2 constituent, and this is responsible in other locations for double high waters and double low waters. And because Devonport is in the English Channel, there is some amplitude in the M4 constituent. You can see there are many constituents, but most of them have got a much smaller contribution to the overall tide than those main semi-diurnal constituents. Further down, we've got how much percentage of the energy within the tide is attributed to each constituent, and you can see that that's dominated by the lunar semidiurnal tide. So we've now got our coefficients that have been calculated, basically how much of the tide can be accounted for by each of the different constituents, and then we can use the second function in the UTide toolbox, the reconstruct, to actually create a new set of predictions. So we can say data.elevation_fit, which is now our predicted elevations, equals UT reconstruct, and then we give it the times and then the coefficients. So the times are data.date time, and it should be data 2000 because we're working from the year 2000 data, and then the coefficients that we just calculated. If I run this, it will then calculate a prediction for each of the times within our year 2000 data set. I can then adapt my plotting function so that it plots the additional data. Now, because there were gaps in the original elevation data, and I've now got a continuous set of data, I'm going to plot the fitted data first in red, then I'm going to hold on, and then the second plot will be the original one, which will be in blue. And so I can save that, and then I can rerun it with my plot command. I had to exit MATLAB to install you need the statistics toolbox to run the UTide version, so I need to just re-add the mfiles folder to my path, and we're in the UTide folder, so I can then plot the data. I've called that data.elevation_fit, so I've misnamed this output, so I need to clear data to get rid of that error, and then data.elevation_fit is the command, but I actually need to name it correctly as data 2000.elevation_fit. Redo that calculation, and then I can redo my plot, and now you can see that I've got my tidal prediction printed in red and the actual measured data points in blue. And if I zoom in on some of this data, you can see that there's a small offset between the predicted and the actual measured data. And this is down to the variation that you get in non-tidal contributions to the sea level, and these are mostly associated with atmospheric pressure, but also with wind pushing water on and offshore, potentially leading to storm surges. So the difference between the measured data and the predicted data tells you how big the non-tidal component is, and that's called the residual. And to show the residual, we can very simply create a new figure. So to do this, I'm going to copy that and then paste it, and I'll then create figure 2, and what we're going to do is to plot the date time on the x-axis, and then we're going to plot the real data, which is data.elevation, and then take away data.elevation_fit, and we'll use let's call it a magenta line in this case. I don't need the hold on because there's only one data series, but the Y label is now the residual. So if I save that, go back to the command window, and then I'll rerun my plot command, And so I've now got two plots. I've got the predicted and the measured, and then in this case I've got the residual. Now, the follow-up for this piece of work was to, so this is the residual that we've just calculated, and the follow-up is to repeat the analysis for 2 more years of data. And not answering this question, but just taking note, how do the tidal constituents vary between the years? So just have a look at those values, and then it's produced a plot showing how the residuals change with each year. So it's basically to repeat this process with different years of data and produce 2 more of these plots. Then you might want to plot them as subplots within the same figure window, so that you could then directly compare them side by side to see how the residuals change. So to rerun the data, you need to do your data loading function. So that was the loading. I've already loaded data 2015. You then need to rerun that calculation of the coefficients, but with the new data, so that's with the, in my case, the 2015 data. So it will rerun that calculation. And then you can rerun that calculation of the fit, but now using the 2015 time base and outputting it into the 2015 data array. And then we can do our new plots with the 2015 data in this case, and you can see that that was a more continuous data series, so that there was fewer gaps in the available data. Now I should have pointed out that when I was running this load data function, if I run it from within the utide current version folder, it's not going to work. So it will complain about this fgets doesn't work, and that's because it can't load up this data file, and that's because I need to change my working folder back into the data folder, at which point this will then work and I can load up another one of these data files. While we're talking about loading data, the other thing that I can't do is click the run button here. Now, when you're working with scripts, you can click run and then that will run the full list of commands. The problem is I can't click run here. I'll show you. If I click run, then I get an error and it says not enough input arguments, and that's because we've written this as a function and we need to tell it which data that we're actually going to plot, or similarly we need to tell it which file we actually want to load the data from. And so you can't use this run button when you're working with functions. You can only use the run button when you're working with a script file.